here we are again, and we are discussing the history of the atom, part 3. When we left off last time, we were talking about Louis de Broglie, and I did notice that, yes, I am spelling challenged. He was not royalty, he was what? Royalty. Sorry about that, folks. I do indeed know how to spell. Sometimes I just get so excited about the chemistry that I forget about spelling. And what did we say about de Broglie? De Broglie came up with the idea that electrons have wave particles, that electrons exhibit a wave particle duality, and that they exhibit these wave characteristics in their when they exist around the nucleus, right? Good. Now, the next place we want to go is a guy named Wolfgang Pauli. Pauli is from Austria. He was born in one of my favorite towns in the world, and that is Vienna. A great place for you all to go visit someday in life. And Pauli was one of Bohr's students. Okay, Pauli worked with Bohr at one time, and remember, other people worked with Bohr. Bohr was a great mentor. People loved working with him. Oppenheimer, Pauli, Heisenberg, these guys all spent time with Bohr. Good. And Pauli is an interesting character. He is known for three things. He's known for the Pauli neutrino, neutrino. That's a particle, a chargeless particle that he predicted and would exist. And in fact, in the 70s or 80s, we did indeed find that it existed. He's known for the Pauli effect. Now, the Pauli effect is kind of a crazy thing here. There are really two types, and you really don't need to know the Pauli effect, and you don't need to know the Pauli neutrino. It's just something kind of interesting about the guy. Pauli was a brilliant theoretical physicist, which meant he could do lots of good things with numbers, right? But he was a terrible experimental physicist. He seemed to break everything he came in touch with. In fact, his effect was so strong, his inability to do experiments correctly was so great that just his presence could make experiments fall apart. And so the Pauli effect is the closer Pauli was to a lab, the more likely the lab would break. So the closer Pauli was to the lab, the more likely something would break. In fact, one time they were going to pull a joke on Pauli, and so they set up a chandelier, a glass chandelier in a room, and they had it hooked up to the door so that when Pauli opened the door, the chandelier would fall to the ground and break. And then, of course, all the physicists over here would laugh, right? They go, ha 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 ha, the Pauli effect. Well, what happens? Pauli walks into the room, and since everything Pauli does ends up going wrong, every experiment breaks, what happens? He walks in and nothing happened. The chandelier didn't fall, which is a perfect example of the Pauli effect. Since they planned for it to fall, since Pauli was close to the chandelier, what they planned to do didn't occur, and nothing happened. That's a true story. Okay, so that's enough of the Pauli effect. Now, what is it that you really need to know? Well, here's what you need to know. This is called the Pauli exclusion principle. And the Pauli exclusion principle has to do with the number of electrons that can be at a given orbital. Now, at one time this was before orbitals were determined, but we've adjusted it to that. So here's a statement of the Pauli exclusion principle. There are no more than 2 electrons per orbital, and each of these electrons, each with opposite spin. Okay, and this will be much more helpful when we talk about electron configurations. But this is the Pauli exclusion principle. No more, there are no more than 2 electrons per orbital, each of which each with opposite spin. And what do we mean by spin? Yeah, it's really a tough thing for us to understand, but the analogy we can use is that electrons spin kind of like tops, and one spins in one direction and one spins in another. Now that's the analogy, that's the model. It's not reality, but that's at least a way for us to think about it, okay? So that's what Pauli came up with. And Pauli came up with this when he was 25 years old. Can you believe that? 25 years old. That's like 9 years older than you all. And then he wins the Nobel Prize. He wins the Nobel Prize in 1945, which seems late, but that he won that for his contributions, the Pauli exclusion principle, as well, I think, as his work with the neutrino. Good. So from there, who's next? A guy named Erwin Schrödinger. And Erwin Schrödinger is really more of a theoretical physicist. Yeah, and he was a brilliant mathematical mind, really. And he comes up with the idea of trying to mathematically support de Broglie. De Broglie said what? De Broglie. He said, hey, electrons act like waves. Well, he didn't work quite as much on the mathematics. Schrodinger did. Schrodinger took the equation for a standing wave and started working with that to see if he could predict the Bohr um, atomic radii based on Bohr's energy levels. And he was able to do that. And he came up with something called Schrodinger's equation. Okay, and this is probably the most important quantum equation in the world today, Schrodinger's equation. And what did it do? It supported de Broglie's idea that electrons have wave properties. And based on this, we can come up with the shapes for our orbitals, okay? Our orbital shapes. And let me try to hold off on, what exactly is an orbital and what do I mean by orbital shapes. I'll get into that in a later lecture later today. But for the time being, let's just accept these two contributions from Schrodinger. Schrodinger was relatively old when he did this. He was 39 years old. He had been out in Arosa, Switzerland. He was having an affair with his mistress, and he came back with this great idea. Not that I support having affairs with mistresses, but hey, the Swiss Alps are pretty cool, and so you go there, you think a little bit, and you come back, and you have a great idea. And he won the Nobel Prize in 1933. Good. And one other interesting thing about him is Schrodinger came up with this. He and Einstein were fighting against Bohr and Heisenberg about this whole idea of quantum uncertainty. And so to try to win that fight, he came up with a thought experiment called Schrodinger's cat. Schrodinger's cat. And so if you want to know more about Schrodinger or about Einstein and Schrodinger's intellectual battle with Bohr and Heisenberg, then check out Schrodinger's cat. And speaking of Heisenberg, he's our last guy here. Werner Heisenberg. He's a German. Yes. A young guy. You can see that. He was extremely intelligent. Another one of Bohr's students. Yes, he was a student of Bohr's student. And Heisenberg came up with it's called the Heisenberg, he didn't name it that, but others did, the Heisenberg uncertainty principle. Okay, the Heisenberg uncertainty principle. Now, what he did is he took some math and ran it out, and he figured out that the more you knew about an electron's position, the less you knew about its momentum. And so what he concludes is one cannot know, or determine is a better word to use, one cannot determine both the position, and he said momentum, but we're going to go with velocity, position and velocity of an electron. Okay, now what are the practical implications for us? That means what? Uh, we cannot know exactly where an electron is. The best we can know is we can only know the most probable location of an electron, and that is what we call the most probable location of an electron. Is that word I've been using. It is called an orbital. That is what an orbital is. It is a most probable location. Now notice, it is not some kind of a track. It is not some kind of electron holder. It is just a probability. And that's kind of difficult to understand. But let me take a minute and talk about that. Okay, so let's say that we take a two-dimensional plot of an electron's probability, and we take Schrodinger's equation. Okay, so here's Schrodinger's equation, right? And we said from Schrodinger's equation, we can get the shape of an orbital. So what do? We put input in here, meaning we put some kind of numbers in here, and each dot would represent an electron's possible location. So I put some dots in, and there's an electron here, 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 and maybe one way over there, and here, 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 and one over there, and here, 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 and one over there, and here, 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 and one might be way over there, and here, 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 and maybe one down here. Now, when I look at this whole plot, what does this kind of look like? This kind of looks like what? It looks like a circle, or if it's three-dimensional, it would be a sphere. A sphere. It would be a sphere. Good. Now, is that really like a circle that holds electrons? Does this hold electrons? No, 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 it doesn't. No, it doesn't hold an electron. It is just a plot of the most probable location of where that electron would be given Schrodinger's equation. Okay? I know it's a difficult concept, but what I want you to understand is that an orbital is not some kind of train track that electrons float on, and it's not some kind of shoebox or any other thing that we stick electrons in. An orbital is this idea of where might I most likely find an electron. Okay, good. We'll use Schrodinger's equation later and come up with more shapes in our next lecture, but this is where we're going to stop on, at least on Heisenberg today. And once again, Heisenberg said the most probable location of an electron is the orbital. And let's add one other thing. Sorry about here. What if I have a collection of orbitals? If I have a bunch of orbitals, a collection of the most probable locations, a collection of orbitals, what do we call that? We call a collection of orbitals the electron cloud. There we go. So a little more nomenclature. All right. So really, that's about where we stand on the quantum mechanical model for our atom. So let's summarize the quantum mechanical model of the atom. Okay, I said electron, but of the atom, right? So what is really our best thinking of what the atom is today? Number one, there is a massive positive nucleus. Great. Hey, who gave us that? That came from Rutherford, right? 2. Electrons exist at specific energy levels and exhibit wave characteristics. This is a little different than my note state, but it's the same idea. I have a hard time talking about electrons traveling like waves around the nucleus, but they exist at specific energy levels. Now we can say around the nucleus. I'll buy that. Around the nucleus and exhibit wave characteristics. Okay, so who gave us these two ideas? Well, traveling or existing at specific energy levels, that would be whom? That would be Bohr. Exhibiting wave characteristics, that would be de Broglie. Yeah. C. 3. For an electron to jump to a higher level, what must happen? The electron must, for an electron to jump to a higher level, let's get this English right. For an electron to jump to a higher level, the electron must absorb a quantum of energy. I'm going to just put a big E. And for an electron to drop to a lower energy level, the electron must do what? Emit a quantum of energy. Okay, so who gave us these two ideas? It's extended here. Who gave us this idea of quantum? Well, the quantum came from Planck, right? And the idea of electrons dropping and raising requiring quantum came from Bohr. So I'd give credit to Planck and Bohr for number 3. Number 4, there are no more, let's put it that way, no more than 2 electrons per orbital. And that would be whom? That would be Pauli. And 5, the orbital shapes are based on Schrodinger's equation. And that's easy. Who is credited with that? Schrodinger. And number 6, we can only know the most probable location of an electron. We cannot know exactly where it is. And who gave us this beauty? Heisenberg. Good. And this whole idea here about we can only know the most probable location, that drove Einstein crazy. He hated that idea, and he once said famously he didn't believe that God played dice. Okay, good. So that's really the big 6 for our quantum mechanical model. And I just want to take a few moments to point out 2 other things. First of all, I want you to understand this, right? Thomson was working, right? And who worked for Thomson? Rutherford. And then Rutherford, who worked for Rutherford? Well, And who also worked for Thomson? Well, Bohr worked for Thomson, and Bohr worked for Rutherford. And then who worked with Bohr? Well, we have Pauli, who worked with Bohr, and we had Heisenberg, who worked with Bohr. And what do you notice here? That to get these great ideas, you have a whole group of people, brilliant people who are working with each other and exchanging ideas. And it's not like science breakthroughs occur in dark closets. Great science occurs because there's an interaction between brilliant minds. These people are talking all the time with each other, and they learn from one another, and they're exchanging papers, and they're analyzing papers, and that's how great science occurs. It's to kind of paraphrase Newton. He said something along the lines that if I see beyond what others see, it's only because I stand on the shoulders of giants. Meaning, if Heisenberg can come up with a great idea, it's only because he learned something from Thomson, and he learned something from Rutherford, and he learned something from Bohr. Great foresight, great breakthroughs come from learning from other people. That's number one. Number two, I want you to take a look at the ages of these people. Thomson was 41 when he had his great idea. Rutherford was 40. Bohr, 28. D. Broglie, 32. Pauli, 25. Schrodinger, 39. And Heisenberg, 26. If you take the average of these people, their average was 33 years when they had their great ideas. In fact, Einstein, his most brilliant year was when he was 26 years old. Okay, so what does that mean for us? Think about it, folks. You all are closer to brilliance, to mental brilliance, than I am. You all are closer to mental brilliance. You guys are 10 years from Einstein's greatest output. You're only what? 17 years maybe away from 33? So the question then is, if you guys are closer to brilliance, who is going to solve the world's problems? Who will solve the problems? If you're relying on me, if you're relying on your old parents, if you're relying on someone in their 50s and a politician or a president to solve your problems, hey, you're looking at the wrong generation. The generation that is going to solve your problems, that are going to solve the problems that we have right now, are you all. The people between 16 and 36 are going to solve these problems. And if that's the case, what's the challenge to you? The challenge to you is you better get started. Get started now. Use your mind. Read, learn everything you can. Be a sponge. Don't sit home playing Madden all the time. Learn something. Get excited about the world. Get excited about the problems and start solving the problems. Okay, that's my little sermon to you, and I hope you understand now something about the quantum mechanical model. And that's really about it for now. See ya.